Okay, so our next section here is actually down here 3C, talking about mathematics and measurements. Mathematics and measurements. So we're going to take our measurements and then talk about what we actually do with them. So the first thing we want to mention here is that, we make measurements in science and they're really useful, but the reason they're useful is we like to plug them into nice formulas. So this, of course, is a bunch of crazy formulas, lots of stuff there. But some you might see in this class actually. Density we've already seen. Density is equal to mass over volume. Another one you've probably already run into is the idea of a volume, specifically of a cube. So a cube is like perfect squares on each side. In that case, if you take the length of one side and cube it, you find the volume of that cube. Okay. One that we'll come across later in the year is this one, PV equals nRT. That's the ideal gas law. It's pressure times volume equals N, which is number of moles, times R, a constant, and times temperature. That relationship holds. So yes, we have these measurements, but we find that there are these constant relationships between measurements that we can find, and so that's really our goal in making measurements, is then to use them in calculations. But then we want to ask ourselves, well, what does that mean about that accuracy and precision that we talked about before? Okay, so when we start to do these calculations and use our calculator, we end up with some issues. So let me take a look at this problem here, and I'm going to actually do that here on my notes. So if we have this calculation, so say we have something and we find its density. Okay, we're finding its density. We've measured the mass, we've measured the volume, and now we're going to calculate the density. Okay, taking a look here, you would say that this number is fairly precise. It's got 2 digits after the decimal. So remember, we've got known digits and an estimated digit. So that means that this the balance we used to make these markings had markings to the 10th of a gram, and then we estimated that last digit. Down here, the volume, okay, our markings had markings of 1 milliliter, and then we estimated the last digit. That's what these two things mean. And as I talk today, instead of answering questions to turn in, I actually want you to just take notes on the specific examples that I do. So this is the first example. Take notes, write down this example, and that's what you're going to turn in. You can either write it out on paper or handwrite it in Notability, okay? Not typed, but handwritten out, okay? So taking a look here, we've got it all set up. So 44, whoops, I'm having some trouble here. 44.03 divided by 5.8. Okay, I do that calculation and I get this number, and you can see this number here. I've written it out. It's a very long number, and I've also got it on my screen in my calculator. It's a very long number. Notice that the units combine, grams per milliliter is our unit, and that's a really long number, right? There's lots of numbers after the decimal. It's a lot longer than these numbers we started with. So yes, numerically this is correct. However, we're letting our calculator think for us here, and when we do that, the problem is that we allow our calculator to determine the precision rather than the real life situation. Okay, this number is way more precise than the numbers we started with, and that's just not right. Okay, so remember, we want to be honest in our measurements. We want to tell the truth. We don't want to ignore telling the truth. So it's important to make sure we're communicating properly. If another scientist sees this number as my calculated number, they're going to think that my measurements that I got this number from were really precise, and that's just not the case here. So let's talk about what that actually means in some specific cases. All right, so the first thing we want to talk about here is what happens when we add and subtract two pieces of measured data. So what happens when we add and subtract two pieces of measured data? Well, the first thing is we know that we've got to have the same units, okay? Think about it this way. You can't add apples and oranges. So you know, if I wanted to add 5 grams plus 10 meters, you would tell me, Miss Bolin, you're crazy, stop. Okay, so this is another example. I want you to write down this example, and this is part of your notes that you'll turn in. You don't have to take extensive notes, just the examples. Okay, so first one was that density calculation. The second one here, 5 grams plus 10 meters doesn't make sense. You can't do that. Okay, you got to have the same units. Now, what if I asked you to add 5 centimeters plus 10 meters? That's a little bit different, because even though these aren't exactly the same unit, they are the same base unit. So we can do this one, but we need to convert first. So if I want to convert 10 meters to centimeters, that means I'll have 5 centimeters plus, and then centimeters, we're just going to move 2 places to the right. So it's plus 1, 0, 0, 0 centimeters. Okay, now when I add them together, I will have 1, 0, 0, 5, and then my final unit will be centimeters. Okay, so I can do that now that I've changed the base unit. So watch out for those prefixes. So just because they aren't exactly the same doesn't mean you can't add them, but you do need to make them the same before you do that addition. Okay, now the other thing we want to look out for is when we are adding and subtracting. How do we know how precise to make our final answer? Okay, that's our question. How precise should our final answer be? Okay, so for adding and subtracting, our final answer should have the same number of decimal places, or places after the decimal, as the data that has the least number of decimal places. So we can only rely on our least precise measurement, whichever one is least precise. So for example, again, this is an example I'd like you to write down. This is something you'll turn in. If I wanted to add these two masses, okay, 1.008 grams plus 16.00 grams. First thing to note is grams and grams, same unit, okay? Now, which one of these is more precise? We see that this one has 3 spots after the decimal. This one only has 2, okay? So the least precise is the second one. Alright, so what we'll do is we'll go ahead and do our addition just like we would in our calculator. Okay, so that would give us 8 there, 0, 0, our decimal falls down, it's 17 out front. Our same unit sticks with us. Okay, so we added those two things together. However, this is now as precise as the most precise measurement, and that's not good. Okay, we need it to be as precise as our least precise measurement, because we didn't know if there's a value here or not. It could have been 7 or 1 or something. We don't know what was there. Okay, so we can't just assume that that 8 is adding to nothing, because that measurement was not as precise. So we need to round to only the second place after the decimal. That's this spot. So I'm going to put a line under it. Notice I want to write down my calculator answer, and now I'm going to give a final answer that's rounded. Okay, the 17 doesn't change, 0.0, and now I'm going to stop with this digit, the second one after the decimal, but to decide what that digit should be, I have to look right. And if that number is greater, 5 or greater, I'm going to round up, and in this case it is, so I'm going to put a 1 there, and then still my units. So my proper answer with correct number of significant digits there is 17.01 grams. Okay, so that's my final answer. But in your work, I still want you to show this calculator version, and then give me a final answer at the end. Circle it. Make sure you have units. Okay, so that's the rule for adding and subtracting. Your data must have the same units, and the final answer should have the same number of decimal places as the answer with the fewest decimal places. Okay, now what if we are instead multiplying and dividing? Multiplying and dividing is a little bit of a different animal, okay? So in this case, your units do not need to be the same. In fact, a lot of times they're not going to be the same, but what they'll do is they'll combine or they'll cancel out, okay? So our units will not be the same necessarily, but they combine. They don't just disappear necessarily. In this case, okay, when we multiply and divide, we're actually going to look at, instead of the decimal places, because when you multiply and divide, decimal places get shifted around. Instead, we're going to look at significant digits, okay? So, for example, if I have a piece of paper that is 11.5 centimeters by 5.5 centimeters, okay, and I want to find the area. Okay, the length and the width are there. Notice they are the same unit in this case, but our final unit will not be centimeters because area is not in centimeters. So to find the area of this piece of paper, we would multiply the length by the width. Okay, so that's 11.5 centimeters times 5.5 centimeters. Okay, and I put that into my calculator. My calculator is going to tell me that this is 63.25, and then my units, since they're multiplied together, they combine to centimeters squared. Okay, now I want to ask myself, how many digits should my final answer have? And what I'm telling you is, multiplying and dividing, we look at significant digits. So we go back to our original values up here and ask how many significant digits are in this value, okay, in this measurement. And this one has 3 because they're all non-zero numbers. That one has 3. And then this one has 2 significant digits, also non-zero digits. Okay, so which one has the fewest? It's this one. So my answer can only have 2 significant digits. So I count from the left. 1, 2. That's going to be my last digit. The 3 is going to be my last digit. So my final answer is going to be 6, and then I look at the 3, I look to the right here. Is this number 5 or greater? It's not, so I'm not going to round up. I'm just going to leave it 3. And then my final unit there, centimeters squared, there is my answer, 63 centimeters squared. Okay, that's my final answer with correct significant digits. Note that if we are multiplying by a whole number, like 2, 3, 5, so if one football field is 100 meters, 5 football fields, you would multiply by 5. That's a whole number, okay? So in that case, the significant digits don't matter, okay? So when we've got a whole number, or when we've got a defined quantity, so that by definition 1 meter is 100 centimeters, I'm not caring about precision there. Okay, the last thing we'll look at is what do we do if we've got a compound calculation, meaning you've got addition, subtraction, multiplication, division, a lot of those, more than one of those in one problem. The key idea here is that you do not round until the end, okay? That's the key idea. Don't round until the end, okay? Don't round until the end. Only in the very end, last step, would you round your numbers. And then when you do that, base it on whatever the last operation was. So if the last thing you do is divide, then use the division rule, use the significant digits rule. If the last operation you do is add or subtract, then use the decimal place rule. Okay, so that's one important thing. So for example, here we're given this picture. Here's a cube. All right. First, to find its density, we first need to find its volume. So all of these are just one significant digit. Okay, multiply them together. Okay, if we rounded this number, we would get 300. Okay, with proper significant digits, but we don't want to do that. Okay, so what we want to do here is keep the 288 until we plug it into the density equation. Okay, mass over volume. All right, so we would get the mass over volume without rounding, 2.083333 grams per meter cubed. And then if we had rounded, we would get only 2, so which is a little bit off. Okay, so keep that in mind. Don't round till the end. That's the basic idea.